All right, folks. Well, welcome back. Hopefully, you were able to kind of go through this idea of hybridization and be able to work through a few of these problems in order to practice and determine then how we can first of all obtain the hybridization of the atoms in any molecule. You have to be able to do that, and from that, then you should be able to also explain then the bonding interactions between those atoms. Okay, and so and then hopefully from that then you can relate also the shape of the molecules as it pertains to the hybridization and also the molecular geometry as well. Okay. So what I'd like to do to finish up with this discussion of hybridization and finish up with our discussion of localized electron models, I want to go over how we can get the bond angle and the hybridization of this particular compound here, this particular molecule here, which I left off, which I asked you to do yesterday afterwards. And so I want to go ahead and go through this, go ahead and work through this one with you that we can talk about this. So let's go ahead and let's pick up with where we left off with. So I did this molecule for you yesterday. Okay. We were asked to find then what we did here is we found not only the hybridization of krypton, but we also found the hybridization of fluorines as well. What you need to be able to do if you see these types of problems on the AP exam is that if they give you the molecule here, okay, either they'll give you the name or they'll give you the formula. In this case, I gave you the formula. Okay. What we have then is a molecule that has two fluorines attached to one krypton. Okay, so what we need to be able to do is we need to be able to draw the Lewis dot structure first. So that's what we have here. We drew the Lewis dot structure for this particular molecule, and that's how we want to start out with this. You want to start out with the Lewis dot structure first. Okay. All right. Then what we did then was we figured out then the number of bonding domains around. I'm sorry, electron domains around this each atom here. And here, so with the krypton, then if you notice, we have three non-bonding domains and two bonding domains here. Okay? And how did we know then that there'd be two bonding domains? That is, how do we know that there would be two single bonds attaching each fluorine to the krypton? Well, you have to remember also then that you have to recall that each fluorine, remember, has to have their octet. There are certain atoms that must have their octet. So we talked about oxygen, nitrogen, carbon, and fluorine. Okay, with the other halogens, now that we've learned then that they could violate their octet. However, fluorine doesn't. So therefore, fluorine has its 7 electrons. It can only take one more. So krypton then, what it does is it takes one of its pairs. So it has 4 pairs. Remember, all noble gases have their complete octet. So krypton will take one of its pairs, split it up, and then form these single bonds with fluorine. Okay. And so you have to make sure you understand that that's how we know then that the krypton and the fluorine are single bonded. Okay, so we'll get back to that in just a moment. Okay, so there's a single bond there, and then so you have the 3 non-bonding domains here. So a total of 5 bonding domains. And you have a 5 electron domains. And so when you have 5 electron domain around this krypton here, okay, so 5 electron domains around that krypton, the electron geometry is going to be trigonal bipyramidal. Trigonal bipyramidal. Now, first of all, so with that said, then when you have a trigonal bipyramidal shape, we saw then that was related to the hybridization that was DSP3. So the good news then with the AP exams that they're not going to ask you, especially this year, they're not going to ask you about DSP3 hybridization. They're not going to ask you about any type of hybridization outside of SP, SP2, and SP3. So make sure you can relate the geometries, the electron geometries around the atoms to the hybridizations, to those 3 kinds of hybridizations. With the higher forms of hybridizations, again, I want to introduce them to you here. You got to make sure you know them. But from my understanding, then on the AP exam this year, they will not ask you about that. Okay? So, but that's how we know that. So, trigonal bipyramidal electron geometry will lead to a DSP3 hybridization. Okay? And so, with that said, then hopefully with the molecular geometry, you see that it's going to be linear. 3 atoms are going to be all in a line here, and that's in accordance with the trigonal bipyramidal electron geometry here. Okay, so you got that linear geometry here. Now, with that said, then the hybridization on the fluorines then, drawing the Lewis dot structure for each one of these, then they have 3 non-bonding domains and 1 bonding domain, which gives you a total of 4 electron domains around each fluorine, which means that it's tetrahedral electron geometry, sp3 hybridized around each Okay? So you have an sp3 hybrid orbital overlapping with one of the d sp3 hybrid orbitals for krypton. That overlap is going to be a linear overlap where the two hybrid orbitals fall along a line. So that's how we were able to determine that this bonding interaction is going to be a sigma bonding interaction. Finally, when we talk about how do we know then that this bonding domain, and this bonding domain falls into one of these five hybrid orbitals? We know that because all 5 electron pairs, whether they are bonding or non-bonding, are going to be degenerate, and the only way you can obtain that degeneracy for those 5 is that all 5 of them have to fall within the same hybrid orbitals. Okay, all right. So make sure you can review that. Okay, make sure you can recall how these hybrid orbitals form. So make sure you come by and see me, folks. I didn't get a chance to see anyone yesterday, so make sure you come by and see me to get that extra help on reviewing, understanding these hybrid orbitals. Okay. All right. So with that said, then we're going to draw this molecule here, krypton tetrafluoride. Now, drawing out this structure here, hopefully you recognize then that with krypton tetrafluoride, and I'm going to go ahead and move this real quickly. Oh, sorry. Okay. Krypton tetrafluoride, then each of these fluorines have to be single bonded, okay, single bonded to the krypton, okay. And so let's go ahead and draw this in. So with that said, then hopefully you recognize then that in order to get in order for krypton to accommodate 4 fluorines, okay, it's going to have to take one of these lone pairs also and separate them out, split them out. Okay, so with that said, then let's go ahead and draw the structure for krypton, the Lewis dot structure for krypton tetrafluoride, each single bonded to the fluorine. So there it is. There are our 4. But however, remember, there are still 2 lone pairs that krypton has. And so there's going to be then, so make sure you keep that in mind. And I'm going to draw the fluorines here. Make sure you draw the lone pairs in for the fluorines, and we'll go ahead and do that as well. Okay. Each fluorine has its 3 lone pairs. Okay. Okay. All right. So with that said, then let's go ahead and describe what we have here. Well, let's go ahead and describe what we have here. Okay. So we have a molecule in which the krypton this time, okay, it has 1, 2, 3, 4, 5, 6 electron domains. Okay, it has 6 electron domains around it. Okay, so you have then 6 electron domains. Okay, as opposed to 5 here. So make sure you keep that in mind, how we get this. Okay, so again, four bonds have to form, okay, which means then krypton has to take one of these pairs. It doesn't matter which one of these pairs here, split them up to form the remaining 2 bonds there. So you have then 1, 2, 3, 4, 5, 6 electron domains. The electron geometry in this case then is going to be octahedral electron geometry. And so with that said, then an octahedral electron geometry leads us then to a hybridization here for the krypton. Then the hybridization here is going to be D2sp3. The other way we can think about this then, if you're given that information, all 6 of these electron domains are going to be degenerate, and so therefore the only way that you can have all 6 pairs being equal in energy is if they all occupy hybrid orbitals that are all equal in energy. So you have here 6 hybrid orbitals. So there's 3. D2sp3 will give you 6 hybrid orbitals. Okay. These electron pairs will fall into each one of those 6, and so that all 6 electron pairs will be degenerate, equal in energy. Okay. Or again, there's that table that I gave you. Make sure you memorize that table. And octahedral electron geometry will always be related, correspond to a D2sp3 hybridization. Okay. All right. So with that said, then hopefully then with the fluorines, you recall then again 4 electron domains here. So each fluorine then is going to be sp3 hybridized. Okay. And with that said, then each of these bonds then is going to represent each one of the single bonds here. It's going to be a sigma bonding interaction. This time, though, the overlap is going to be between 1 D2sp3 hybrid orbitals with an sp3 hybrid orbital. You'll see that overlap here. It's going to be, again, a linear overlap. So therefore, you have then 4 single bonds that are undergoing sigma bonding interaction. You have that particular overlap there. Okay. All right. So with that said, then hopefully you're able to do that. And I'm sorry, finally the molecular geometry here. And let me just go ahead and give you that one. The molecular geometry here is going to be a square planar molecular geometry. Okay. And so which is going to lead us then to a 90-degree angle, 90-degree bond angle between each one of these fluorines, and 180 degrees between each, and then 180 degrees between these 2 lone pairs here. Okay. All right. So with that said, then make sure you review this, folks, and I will include this slide for you as well. So make sure you review this and come by and see me, okay, and get any questions that you may have answered in order to get this done. Okay. All right, so let's go ahead then, and let's continue on with our discussion of the, finish up with our discussion of the localized electron model, and that is, it works pretty well. The localized electron model does a pretty good job of explaining geometries. That it does an excellent job of explaining geometries. It helps us to understand how the bonds, the shape of the molecule will correspond to the properties. Later on that we'll talk about hopefully a little bit next week. I'll post the chapter 10 material, folks, but I'm going to go through chapter 10 fairly quickly. But I want to finish focus on a little bit more photo electron spectroscopy, which is going to be at the end of this chapter. And then I want to talk about a little bit of the chapter 10 material, and then we'll wrap up with that. Okay. The localized electron model does a good job of explaining geometries, which will allow us then to discuss these macroscopic properties of these molecular compounds as well. But there are flaws. There are flaws in this particular model. Okay, and the first and the most obvious flaw then is that the localized electron model predicts then that the electrons will stay localized between 2 atoms. When we talked about hybrid orbitals, remember the sigma bonding interaction assumes then that the electrons are going to be shared between the two atoms, okay, within that particular overlap. So when you have 2 hybrid orbitals overlapping each other, that means then the electrons stay there and they don't move throughout the molecule. That doesn't quite fit with the quantum mechanical model of an atom. Okay, and that is, remember, with the quantum mechanical model of the atom, we learned then that the electrons they move around. We don't know where they are within a single atom. So therefore, you can imagine then when these atoms are part of a molecule, they have now a greater amount of space to move through. How are we supposed to be able to determine then that the electrons stay between 2 atoms? And so that's the key flaw here. And I want to make sure you understand that that's a major flaw in this localized electron model, is that it predicts then that the electrons are localized. Okay? All right, and so the delocalization, how the localized electron model got around that, as we learned about this, it tries to explain that in terms of resonance. Okay? Now, resonance does a good job. Resonance does a fair job of accounting for that, but what it does not do is it doesn't account for certain other things that we talked about. There's the energetics of a bond itself, and why the bond even forms in the first place. Okay, and so it doesn't really help us. The localized electron model doesn't really help us understand why a bond forms in the first place. Okay? And so that's what we want to make sure we understand, and that's why this is something that the localized electron model cannot do. Hybridization doesn't allow us to do that, but we understand, we remember then that a molecule will only form when 2 atoms get together, and when they get together, they drop down to a lower energy state. But the interaction between the 2 atoms have to be lower in energy than the atoms separate, because if that doesn't happen, then the molecule will not form. Okay, and so the localized electron model does not deal with energetics at all, and that is a major deficiency in this particular model in terms of trying to explain how these compounds form. Okay, so again, localized electron model does an excellent job of predicting geometry, but it does a very poor job. It doesn't mention anything about energetics, and energetics is an absolutely critical part of understanding how molecules and thus bonds form. Okay? We saw then with the when we calculated for ionization energy, when we talked about the lattice energies, we saw then why then two ions would get together to form an ionic compound. They drop down in energy, so we were able to explain the energetics of how ionic compounds form. Up until this point, we have not dealt with the energetics of how molecular compounds form, how these covalent compounds form. And so at this point, then we introduced a new model, a second model that will help us address that issue there. And that is this molecular orbital model. Okay? Now, with the molecular orbital model, the key difference between the molecular orbital model and the localized electron model is that the molecular orbital model treats the molecule as one unit. Okay? One unit comprised of separate atoms, but it's one unit, which means then that these electrons are flowing throughout the molecule as a whole. This is very similar to what we talked about when we discussed the sea of electron models and the metallic bonding that occurs. Okay? And so make sure you keep this in mind then, that what the molecular orbital theory does is it treats the molecule as a collection of nuclei and electrons. And that's going to be very similar to metallic bonding. And make sure you keep this in mind that when we talked about metallic bonding, we talked about a collection of nuclei in which the electrons move throughout that whole set of nuclei. Okay, so make sure you review that. And so we will treat now, so the molecular orbital theory kind of treats these molecules as a collective. It's a collective of nuclei in which electrons are moving throughout the molecule. Okay, and so that means then that that allows then for us to discuss then the delocalization. Okay, the delocalization of these electrons. With the sea electron model, remember we had the electrons flowing throughout. Okay, and so with that said, then to account for that, we have to discuss then how these orbitals change, what these molecular orbitals do, what these atomic orbitals do when they are incorporated into part of a molecule. And so if you understand how hybrid orbitals form, it's going to help you understand how these molecular orbitals form. However, do not mistake hybrid orbitals with molecular orbitals. Hybrid orbitals refer only to two atoms, okay, two atoms and their interactions with each other. Okay. The molecular orbitals here represents then a brand new set of orbitals that is shared throughout a molecule. Localized electron model, the atom, and the hybridization of an atom. The molecular orbital theory, the molecular orbital model, deals with these molecular orbitals, which is formed when a molecule forms. Okay. All right, so with that said, then those are the key differences. And then finally, the main difference here is you get a delocalized rather than a localization of the electrons. Okay. All right, so taking a look then at the localized electron model, okay, and make sure you remember this here. With the localized electron model, we talked about how each one of these atoms here, okay, each one of these bonds here form as a result of the overlap of orbitals. Okay. In this case, then we have a 1s orbital from hydrogen overlapping with an orbital, an sp3 hybrid orbital from carbon. And remember what we have here then, this particular bond here is going to be two electrons that are being shared, one electron from the hydrogen, one electron from the carbon. Remember, carbon then has one electron now in each of the sp3 hybrid orbitals. And so this is going to be a sigma bonding overlap. Okay, this is a sigma bonding overlap in which two electrons sit between these two atoms here. Okay, so these two electrons here, make sure you understand, in the localized electron model, these two electrons stay where they are, and it's the sharing of these two electrons between the carbon and the hydrogen here that allows then for this bond to form. Okay, so therefore the bond here, this interaction here, the electrons are localized. They stay in one place. They don't move around. They don't have the option to move from one location to another. Okay, and so what happens here is this interaction is a result of carbon here. Now, again, hydrogen doesn't hybridize, it doesn't change, but the single carbon atom here taking its s orbital in the atomic state and hybridizing with the p orbital, changing it into these sp3 hybrid orbitals, and then from there, then it uses those hybrid orbitals to form these bonds here. Okay, all right. So what the localized electron model does is it treats each atom separately, and the interaction between those atoms as a separate interaction. Okay, so this sigma bonding interaction here is only between this hydrogen and this carbon. This sigma bonding interaction here is only between this carbon and this hydrogen. This double bond here, which is, remember, a sigma bonding interaction plus a pi bonding interaction. Okay, pi bonding interaction here. Okay, That interaction, these two here are only between the two carbons. Okay, so essentially what we have here then is we have then separate atoms being connected together to form this particular molecule. Okay, and so that's what we have, and that's what makes this model different. Okay, and so let's go ahead then and let's take a look at what happens when we transition to viewing the molecule as a single entity. The localized electron model doesn't view the molecule as a single entity. What it does view then is separate atoms interacting with one another in this whole unit. Okay, so you have then a bunch of separate interactions, that holds these atoms together to form the molecule. That's the localized electron model. What the molecular orbital theory does here, and this is what you want to make sure you understand, is that the separate atoms, they take their atomic orbitals, they bring them together, and they mesh the atomic orbitals together. This is why this is similar to the hybridization, but this is not hybridization. This is not hybridization. You do form different orbitals here, but these orbitals now are not shared between two separate atoms, but these orbitals are shared throughout the molecule. All of the atoms will be encompassed by these molecular orbitals here. And so I'm running a little low on time here. I'm going to go a little bit over here, but make sure you understand then that what's happening here is that, for example, I have two separate p orbitals here. These are the atomic p orbitals. What will happen then is the molecule will take the separate p orbitals and they will merge them together to form what are called these molecular orbitals here. These are molecular orbitals. Okay? These are molecular orbitals. These are orbitals that form when atomic orbitals combine together to form these molecular orbitals. The key difference between the hybrid orbitals and these molecular orbitals here, the hybrid orbitals stay localized between two atoms, but furthermore, with the hybrid orbitals, it's one atom taking its atomic orbitals and hybridizing them and making something new. With these molecular orbitals, it is two atoms sharing their atomic orbitals and using those atomic orbitals to come up with something new. Okay? And so that's going to be your key difference in understanding, and that's the key difference in between hybridization and what's going on here. Okay? Hybrid orbitals involve only one atom. One atom takes its atomic orbitals and hybridizes those together, mixes them together. With these molecular orbitals here, you have two or more atoms getting together. And for our discussion now moving forward, we're only going to focus on two atoms, but two atoms getting together and mixing their atomic orbitals together. Okay, and that's going to be key. And so with that said, then what will happen is when you see that mixing occur, what will happen is the nuclei then will still be there. Each one of those nuclei will still be there, but the electrons now are free to move from one nuclei to another, okay, which is very similar to and very similar in model to this metallic bonding here. So this is the metallic bonding that we talked about, okay. The metallic bonding here, which represents a sea of free-flowing electrons. We have then the nuclei getting together. Now the key difference here with the metallic bonding versus the molecular orbitals here is that these atoms here, they don't change their atomic orbitals. They don't change, they just get together, and then the metal atoms, they take their valence electrons, and the valence electrons now are free to move from one nuclei to another. Okay, so that's different. That's different from the molecular orbital here. But the idea here then is that you have a collective of nuclei in which these electrons, these nuclei now share their valence electrons. Okay, so that's what's happening here. But we're taking an extra step, and we're saying then now that in order to share these electrons, what these atomic orbitals, what these atoms do is that they take their atomic orbitals, blend them together to form these molecular orbitals here. So these then represent two molecular orbitals that form when two p orbitals get together. Okay. So what we're going to do on Monday, you know what I'm going to do is I'm going to, since we're really strapped for time now, I'm going to post two videos over. I'm going to record two more videos over the weekend. Please make sure you watch them. I won't require that you turn in any work for them, but please do watch them so that on Monday then we can wrap up with our discussion of molecular orbitals. I'll review this. I'll review what we do over the weekend with you on Monday. But watch the videos, please. Please watch those videos over the weekend. I'll post one on Saturday and one on Sunday. Please watch those videos so that on Monday then we can hopefully get started with the discussion of photoelectron spectroscopy, and then continue on and try to wrap up with the discussion of intermolecular interactions in chapter 10. Okay. All right, folks. So please make sure you watch the videos on Saturday and Sunday, okay, and get the work done. And then on Monday we'll go ahead and we'll continue with photoelectron spectroscopy. Okay. All right, folks. So I will hopefully see. Hopefully you'll watch the videos over the weekend. Don't wait till Monday to watch the videos. Okay. And then that way so we can continue on Monday with the new material. All right. Bye, folks.